Aero 320 Controls Project by Bob Comstock and Sergio Rodriguez.
Remote control aircraft, or RC aircraft, have a control system that consists of a transmitter that sends signals to a receiver that sends an output signal to servos. There's no feedback in this system aside from pilot observations, so there's no stability control. However, a gyro can be added to add some element of stability to the orientation of the aircraft.
Remote control aircrafts are composed of the remote and the actual aircraft. To control the aircraft, the pilot must physically move the analogs on the controller. The movement will be then transmitted to the aircraft via radio frequencies. The plane receives that radio frequency as an input and output movement to the actuators. In this case, servos are typically used to move the control surfaces of the aircraft. As a result, the plane's trajectory is a direct outcome of the pilot's input command through the controller.
An RC aircraft without stabilization uses the input from the pilot through the transmitter and receiver as a direct output to the actuators on the aircraft. Considering there is no feedback for the control, this is an open-loop system with the pilot's observations being closest to any form of feedback to the control system. So for a quick example, this video, we can see that the pilot's movements acting as an input are getting directly translated to an output on the control surfaces of the aircraft.
A plane that has a stabilizing mechanism has a closed-loop feedback system. The system works by initial input by the pilot that is converted to the servo movement. The gyro then uses the previous outputs to then send it back as an input to maintain the previous trajectory.
As for the wiring of the system, the receiver is usually directly connected to the servos, but with the addition of a gyro, it's placed between the receiver and the servos. Utilizing the built-in accelerometers, the gyro will measure and correct any changes such that the plane will maintain the last orientation it was in.
On the left of this video, the RC plane utilizes a built-in stability system to maintain its current orientation. On the right, there is no stabilization, so the pilot must do his or her best to make the correction. As you can see, the right plane is wild. Here we have a plane that has its own frame. The x-axis is parallel to the fuselage, the y-axis is parallel to the quarter length, and lastly the z-axis is orthonormal to both the x and y axes.
The dynamics of this system can be modeled with the second-order differential equation with a solution that's a mix of sinusoidal and exponential functions. In the graph shown, y assesses the target or desired value or location, such as an angle, that the gyro wants to be at for one of the three principal axes. Depending on the gain of the system, the solution can be either underdamped, where the damping factor zeta is less than 1, critically damped where zeta equals 1, or overdamped where zeta is greater than 1. The graph shown is an underdamped system with the zeta less than 1. Here we can see the two examples of the system being critically damped and overdamped, zeta being equal to 1 and zeta being greater than 1 respectively. This parameter of zeta can be controlled by adjusting the gain on the gyro. So overall, RC aircraft usually utilize an open-loop control system for pilot input. However, a gyro can be utilized as a second input in a closed-loop feedback system to maintain stability. This system can be modeled with the differential equation, which is a solution of sinusoidal and exponential behavior.